In the Linux kernel, a driver is a compiled piece of software. It acts as the bridge between the hardware and the software. It tells the kernel how to initialize the device, how to exchange data, and how to react to events. When a device and its driver are registered in the kernel, a binding occurs. The probe function is then invoked and makes the peripheral truly functional. Today, we are going to see how this mechanism works for devices that are not connected to buses providing auto-discoverability mechanisms. Before we start, I just want to mention that this video contains a lot of abstraction and simplified explanation to make the topic easier to understand. So, if you are familiar with this subject and have constructive feedback, feel free to share in the comments. In embedded architectures, many devices are attached to buses that do not provide auto-discoverability mechanisms. This is the case for I2C devices, SPI devices, USB controllers, for example. But a device must be described and passed to the kernel so that it can be registered and then bound to its driver. On x86, the hardware description is in ACPI tables and is loaded by UEFI. On most embedded devices, the hardware description is stored in the DTB and is loaded by the bootloader. DTB actually stands for device tree blob, and I will focus on this method because it is now used by most embedded-oriented architectures running Linux, such as ARM64. So when we power up the board, the bootloader loads the kernel and the device tree into memory. But before going any further, it is essential to understand where the DTB comes from and how it provides the kernel with hardware information. Let's take an example. The I2C protocol relies on a master-slave communication model. Here, the slave is an Atmel EEPROM, and the master is the I2C controller. Let's say that the EEPROM is attached at slave address 0x50 on the I2C controller. Inside the device tree source file, the Linux engineer describes it as a node. The compatible field is very important. It provides hardware information, vendor, model. This property is used during the driver matching process. So the EEPROM talks to the I2C controller. The CPU talks to that controller through the L4 bus, and L4 itself sits on top of the main interconnect called OCP. As a result, the EEPROM appears as a subnode of the I2C controller, which itself is a subnode of the L4 interconnect, and L4 is a subnode of the OCP interconnect. This hierarchy is exactly what you see reflected in the device tree. As you can see, the USB controller does not have subnodes. This is because USB buses provide dynamic enumeration. So, the device tree is a true representation of the hardware, mimicking the actual hardware topology. If another EEPROM is connected, it will be described as an additional subnode of the I2C controller. Once the device tree source is completed and describes the entire hardware topology of the board, it is compiled to produce the DTB binary. Sometimes it is also called the FDT, which stands for Flattened Device Tree. The FDT contains multiple sections. The most important ones are the structure block and the strings block. If we compare the DTS with this structure block representation, we can see that the FDT is a monolithic flat representation. This is why it is called a flattened device tree. In the Linux kernel, every device is represented by a struct device. So how do we go from an FDT to such a representation? Early during the boot process, the kernel allocates memory where the FDT is unflattened. During this step, the devices described in the FDT are converted into a tree of struct device node. These device nodes are later used to instantiate the corresponding struct device. Let's take a look at the unflattening process. In our example, we start with a struct device node named /, which represents the BeagleBone blackboard. Then, child objects are created, such as the SOC node. Next come the child nodes of the SOC, which include peripherals like the I2C controller. Finally, the devices attached to that bus are represented as child nodes of the I2C controller, in our case, an EEPROM. Note that if there were an SPI controller, it would also be represented at the same level as the I2C controller, as another child of the SOC. So we end up with a tree of struct device node, faithful to the hardware topology. As I said earlier, devices are represented by a struct device which has not been created yet. At this stage, we only have struct device node. So the question is, how do we go from one to the other? One of the first types of devices that get registered are platform devices. In Linux, a platform device is typically a top-level device tree node with a compatible property, or a child of a node marked as simple bus, which basically means everything under here is memory mapped. Some I/O devices come with onboard memory. Registers, for example. Memory-mapped I/O works by exposing part of that onboard memory to the system. The CPU can then read from or write to it as if it were just another region of memory. The memory-mapped approach gives I/O devices their own specific region within the system address space. From the CPU's perspective, communicating with these devices is no different from reading and writing variables in memory. For each child node of the root, the kernel calls the function open firmware platform bus create. It checks whether the current struct device node has a compatible property that matches a given match table. In particular, simple bus. Two cases can happen. If a device is created and it represents a platform bus, for example a simple dash bus, the kernel keeps going and applies the same logic to its child nodes. If the node is not a platform bus, like an I2C controller, the recursion stops there, and the children are then handled later by the corresponding bus subsystem, such as the I2C core. At this point, our I2C controller has been discovered and is now represented inside the kernel as a struct device. But what about the driver? To understand that, we need to go back in time to when the kernel was compiled. In our example, there are two relevant drivers, at 24.c for the EEPROM, I2C-omap.c for the I2C host controller. When you look at these files, you'll notice that each of them defines a function marked with an init macro. These functions are responsible for registering the driver with the kernel. However, these functions are never called explicitly anywhere in the kernel source. So the question is, how does this code actually get executed? The answer lies in kernel configuration. When we configure the kernel, for example using make menu config, we can choose to build a driver directly into the kernel as a built-in driver. All built-in drivers are statically linked into the kernel image. Their init functions are placed into special sections, and all of these functions are automatically executed during kernel boot. Let's look at this in more detail. In the make file, the value of a variable is resolved by looking at its corresponding option in the .config file. The same process applies to all drivers. Every driver that ends up in obj-y will be built directly into the kernel. During compilation, object files are generated. After that, a thin archive called built-in.a is created. This archive contains the list of object files generated in that directory, along with their metadata. This process happens recursively in every directory. Each built-in.a is merged into the one in the parent directory, step by step, and until we end up with a top-level built-in.a that references all the generated .o files for all built-in drivers. This archive is then used to build vmlinux.a, which will enumerate other additional object files coming from the /lib directory. All these .o files references in vmlinux.a are finally linked into the final kernel image. The init macro is translated into a compiler directive that places the corresponding code into a dedicated .init section of the elf kernel image. At boot time, the kernel executes a series of init calls which run all the code stored in that section. This is how built-in drivers get registered automatically during kernel startup. Let's come back to our example. For demonstration purposes, I will add a few dummy devices and drivers. Once the init function is called, the I2C controller driver is registered in the platform bus driver list. At that point, the platform bus checks whether this driver can be bound to any existing device. To do that, it compares the strings found in the compatible fields of the driver and the device. If they match, the driver is bound to the device. Once the match is made, the driver's probe function is called. This is where the driver maps its registers, sets up interrupts, enables clocks, and performs all hardware initialization. Once initialized, the I2C bus is exposed to the Linux device model by registering an I2C adapter. The I2C core can then instantiate the child devices described in the device tree as I2C clients. The matching method is identical to what I described previously. The kernel compares the strings in the compatible fields of the driver and the device. If they match, the driver is bound to the device. I hope this overview of how non-discoverable devices are probed is clear. You may have noticed that I focused exclusively on built-in drivers. In a separate follow-up video, I will cover the same topic for loadable kernel modules and highlight the key differences in their probing lifecycle.